It's 2 a.m. Your phone is at 4%, and you are crawling across the floor in the dark, feeling behind the nightstand for a charger like your life depends on it. Heart rate up, a little sweat, full survival mode, over a glowing rectangle. Now here's the strange part. That thing you're panicking about, the flat little slab of power inside your phone, is not modern magic. It's a chemical trick that's more than 200 years old. And the deeper you dig into where it came from, the weirder the story gets. Because it starts with a clay jar pulled out of the ground near Baghdad in 1936, a jar that for a few years looked like proof that somebody had beaten us to the battery by 18 centuries. So how did humans actually invent the battery, and why is the honest answer that, in a way, nobody did? Let's get one thing straight up front. The battery is the most quietly ridiculous object you own. You carry a supercomputer in your pocket, sure, but the part that keeps it alive is basically two different metals and some damp stuff in the middle. That's it. That's the whole idea. And that idea has been refined, argued over, and passed hand to hand across dozens of countries and more than 2 centuries, from a physicist showing off for Napoleon, to a public fight over dead frogs, to 3 men who split a Nobel Prize in 2019 for the exact battery you're holding right now. And here's the thing I want you to hold on to for the entire video. The core trick behind that battery has not fundamentally changed since the year 1800. Everything since is just a better version of the same move. Keep that in mind. It matters more than you'd think. But to see why, we have to start with that jar. Picture a dig site in 1936, a village called Kujut Rabu, just outside the ruins of an ancient city near Baghdad. Archaeologists pull a small terracotta pot out of the dirt, about the size of your fist. Inside it, a copper cylinder, and stuck down the middle of that, an iron rod sealed in place with tar. Nobody knows what it's for. A German named Wilhelm Koenig looks at this thing and has a wild idea. What if it's a battery? What if you filled it with something acidic? Vinegar, grape juice, and it made electricity. So people build replicas. They pour in the vinegar, and a needle twitches. The jar produces around 1 volt, a real, measurable current from an artifact that's roughly 2,000 years old. For a while, this was electric in every sense. Books, documentaries, late-night internet rabbit holes, all of it running with the same jaw-dropping claim: the ancient world had electricity, 2,000 years before we thought. They were secretly electroplating gold. We'd been beaten by the Parthians. Except, almost none of that holds up. Here's what the archaeologists actually think. Metallurgist Paul Craddock at the British Museum has pointed out the obvious problem. If these were power sources, where's everything else? There are no wires, no connectors, not a single electroplated object from that time and place that needed a battery to make. No writing anywhere describing an electrical anything. The gold-plating people did do back then used mercury, not electricity. And the real kicker, jars almost exactly like this one, from the same era, show up holding rolled-up scrolls. That copper tube and iron rod, probably just what you'd wrap a sacred piece of parchment around to protect it. One archaeologist put it flatly: I don't know anybody in the field who thinks it's a real battery. Can you make it behave like one? Yes. Was it built to be one? Almost certainly not. And while we're clearing the table, you may have heard an even bolder version that the Sumerians had batteries around 2500 BCE. That one you can throw straight in the bin. There is nothing behind it. The jar isn't Sumerian, and it isn't from 2500 BCE. It's a couple thousand years younger than that. The claim is just a myth that drifted further and further from an artifact that was already misunderstood. So the Baghdad Battery isn't our origin story, but it does leave us with one genuinely useful clue. Because think about what actually happened in those replica experiments. 2 different metals, a splash of something sour, a twitch of real electricity. If a random clay pot can stumble into that by accident, then the fundamental idea behind a battery must be almost embarrassingly simple. So let's answer the obvious question. What is a battery actually? Strip away everything, and a battery is a very controlled argument between 2 metals. You take 2 different materials, one that's a little desperate to give away electrons, and one that's happy to receive them. You put them both in a liquid or paste that lets particles move around, called the electrolyte, and then you connect them with a wire. Here's the part that's genuinely elegant. The eager metal wants to dump its electrons, but it can't just hand them across directly. The only path open to them is the wire, the long way around. So the electrons go marching through that wire, and that marching river of electrons is electricity. That's it. That's a battery. One side gives, one side takes, and you steal the flow in between. Picture a crowded room with a door into an empty room. Everyone wants to get to the empty side. Force them all through one narrow hallway, and that rush of bodies down the hall. That's your current. The battery's whole job is to build the crowded room, the empty room, and the hallway, and then get out of the way. And I cannot stress this enough. From this point on, everything is the same idea. Volta's stack of coins, the battery that starts your car, the one in your phone. Every single one is 2 materials with a difference in appetite, an electrolyte in the middle and electrons forced to take the long way around. What changes over the next 200 years isn't the trick. It's how clever we get at picking the 2 metals. But before we get to the man who stacked those metals, there's a detour most people never hear, and it's where the word battery actually comes from. Rewind to the 1740s, decades before Volta. Scientists could make electricity, but only the crackly, useless kind. Static, the same thing that zaps you off a doorknob. The best they could do was store a little of it in a glass jar lined with metal foil called a Leyden jar. And a Leyden jar had one setting: everything at once. Touch it wrong and it dumped its entire charge into you in a single violent snap. One of the men who first got hit by one wrote that the shock was so bad he would not take it a second time for the whole kingdom of France. That's the problem. Static electricity was a party trick. You couldn't run anything on a jar that either sits there doing nothing or tries to stop your heart. And when Benjamin Franklin wired a bunch of these jars together to store more charge, he needed a name for the group, so he borrowed a military word for a row of cannons lined up to fire together. A battery. So here's a fact to sit with. The word battery is older than the battery. It started as a line of cannons, became a bank of jars that could knock a man flat, and only later got attached to the thing in your pocket. What the world was still missing wasn't storage. It was flow. A steady, gentle, continuous current you could actually work with. And the road to that runs straight through a pile of dead frogs. In the 1780s, an Italian doctor named Luigi Galvani is doing something that sounds deeply unhinged. He's got dissected frog legs and he notices something impossible. When he touches them with metal, the dead legs kick. On stormy days, hanging on an iron railing, brushed with a bit of brass, the legs twitch with every flash of lightning, dead muscle moving. Galvani is amazed. He decides the frog itself is the source. That living tissue is full of its own special animal electricity, a kind of life force stored in the flesh. And you can see why he thought that. The frog is right there, jumping. What else would you blame? Enter Alessandro Volta, another Italian, a physicist, and as crucially, a skeptic. Volta looks at the twitching frog and says, "I don't think it's the frog at all. I think it's your metals." Galvani had been touching the leg with two different metals, and Volta suspected that the metals plus the moisture were making the electricity, and the poor frog leg was just a wet wire twitching in the current. So Volta sets out to prove it. He takes the frog out of the equation entirely, just metals and moisture. And it still works. The electricity was never alive. It was chemistry all along. And then, around 1799 into 1800, Volta does the thing that actually earns him a spot in every physics textbook. He stacks it. Disc of zinc, disc of copper, a piece of cloth soaked in salty water. Zinc, copper, wet cloth, over and over into a tall column. Each little sandwich makes a feeble current, under a volt. But stack 30 of them, and the voltages add up into something strong, and steady, and continuous. Not a spark, not a jolt. A flowing, reliable current you could actually work with for the first time in history. That tower of metal discs is the voltaic pile, the first true battery. It caused such a sensation that Napoleon himself demanded a demonstration, watched this quiet professor turn metal and salt water into endless electricity, and was so impressed he loaded him with medals and later made him a count. And when the world needed a name for the unit of electrical push, they named it the volt after him. Every time you read 9 volts off a battery, you're saying his name. Now, to be fair to the frog guy, history gives them both a medal. Galvani really did discover something huge, that our nerves and muscles run on electricity. Right now, your heartbeat, your every thought, is a tiny electrical signal. Galvani found that. He was right about the body, wrong about the source. Volta got the battery. And honestly, we needed both. Okay, we've got a working battery in 1800. You'd think the rest is a straight sprint to your iPhone. It is not. It's a relay race. Dozens of runners, each one fixing the flaw the last one left behind. Volta's pile had a problem. It faded fast, the salt water dried out, and the metals corroded. Great for a demo, useless for real work. So, in 1836, an Englishman named John Daniell redesigns it into something that holds a steady current far longer, around 1 volts that doesn't collapse on you. This is a bigger deal than it sounds. Daniell's cells became the power supply for the telegraph. The first time in history a message could outrun a horse. The wires that eventually crossed entire oceans and let London talk to New York in minutes, powered at the start by rooms full of Daniell cells. Then things get weird in a wonderful way. In 1839, a Welshman named William Grove builds a stronger cell, and then, almost as a curiosity, runs the whole idea in reverse. A normal battery uses chemistry to make electricity. Grove wondered, what if you used electricity to combine hydrogen and oxygen, and pulled electricity back out as they turned into water? It worked. He'd built the first fuel cell in a battery that runs on gas and breathes out nothing but water. Hold that thought, because 120 years later, that exact idea would fly to the moon on the Apollo spacecraft and show up in hydrogen cars. Back on the main track, the refinements keep coming. In 1866, a Frenchman named Georges Leclanché builds a cell using zinc, carbon, and a compound called manganese dioxide. Remember that recipe, because it is more or less the AA battery still sitting in your junk drawer. That design is over 150 years old. And then the big one. In 1859, another Frenchman, Gaston Planté, cracked something nobody had before: a battery you can refill. Every battery so far died once and stayed dead. Planté's design used lead plates and acid, and when it ran down, you could push electricity back in and reverse the reaction. Drain it, recharge it, drain it again. The rechargeable battery is born. And here's the detail that should genuinely stop you. Planté's lead-acid chemistry from 1859 is the exact same chemistry that starts your car this morning. Not similar, essentially the same. When you turn your key or hit the start button, you are firing up a 165-year-old invention that we simply never found a reason to replace. But notice, everything so far is heavy, wet, and mostly stuck on a bench. Glass jars, sloshing acid. This is not going in your pocket. So how did the battery finally learn to travel? Around 1886, a scientist named Carl Gassner solves it with one deceptively simple swap. Take Leclanche's design, and instead of a liquid electrolyte sloshing around, turn it into a paste. Now you can seal the whole thing in a metal can. It doesn't leak, it doesn't spill. You can turn it sideways, throw it in a bag, hold it in your hand. The dry cell. And within about a decade, that unlocks something you completely take for granted: the flashlight. For the first time, a human could carry portable light with no fire, no fuel, no flame, just a sealed tube and a switch. That is genuinely new in human history. Then, right around the turn of the century, two more runners grabbed the baton. In 1899, a Swede named Waldemar Jungner invents the nickel-cadmium battery, in rechargeable, tough, the ancestor of the rechargeables that powered your old camcorders and cordless drills. And around 1901, Thomas Edison pushes his own rugged nickel-iron version, built specifically for a machine that was, at that exact moment, looking like the future of transportation: the electric car. And that's not a typo. This is the part almost nobody knows. For a brief, strange moment at the start of the 20th century, the future was electric, and then it wasn't. Around 1900, if you walk down a street in New York, a huge share of the cars rolling past you were battery-powered. By some counts, a full third of all cars on American roads were electric, and people preferred them. Gas cars of the era were loud, filthy, and started with a hand crank that could kick back hard enough to break your arm. Electric cars were clean, silent, and you just turned them on. They were especially popular with wealthy city drivers who didn't want to wrestle an engine. So what happened? Three things fast. Someone struck huge, cheap oil in Texas, and gasoline got dirt cheap. Henry Ford's assembly line made gas cars cost half what an electric one did. And then the electric starter replaced the dangerous hand crank, erasing the one big reason to avoid gasoline. But underneath all of it was the battery's oldest weakness. It just couldn't store enough energy to drive very far before needing hours on a charge. The electric car didn't lose because it was worse. It lost because the battery wasn't ready. So the electric car died. For about 100 years. Hold on to that because it comes back, and the thing that resurrects it is the last great chapter of this whole story. Because after Edison, the battery kind of plateaus. For decades, the improvements are small. The truly modern leap doesn't come until the 1970s. And it comes down to one specific element on the periodic table: lithium. Here's why lithium is the holy grail. It is the lightest metal there is, and it is ferociously eager to give up its electron. One of the most powerful electron donors in all of chemistry. Translation: lithium can pack an enormous amount of electrical punch into an almost weightless package. For a battery where every single gram is fighting you, that is the dream ingredient. The problem? Raw lithium is dangerously unstable. So reactive it can catch fire on contact with water or air. For decades, it was simply too wild to put in a product. Taming it took 3 men and about 15 years. In the 1970s, a scientist named Stanley Whittingham, working at the oil giant Exxon of all places, figures out how to slot lithium ions neatly into a layered material instead of using the raw metal. A clever trick called intercalation, like sliding cards into the slots of a rack. It works, but it's still touchy, and early versions had a nasty habit of catching fire. Then, in 1980, John Goodenough finds a far better recipe for one side of the cell, using lithium cobalt oxide, and roughly doubles how much energy the thing can hold. And finally, in 1985, Akira Yoshino in Japan swaps in a safe carbon material for the other side, killing the fire problem, and suddenly the battery is stable enough to actually sell. Sony brings the first commercial lithium-ion battery to market around 1991. And that battery, Whittingham's trick, Goodenough's recipe, Yoshino's safety fix, is the one in your phone, your laptop, your earbuds, and every electric car on the road today. In 2019, all 3 men shared the Nobel Prize in chemistry for it. Goodenough was 97 years old, the oldest person ever to win a Nobel in any category. He helped build the thing you're watching this on, and he lived long enough to collect the medal for it. Just to feel the leap, Planté's old lead acid holds maybe 30 to 50 units of energy per kilogram. Modern lithium-ion holds several times that in the same weight. That gap? That's the entire reason the smartphone exists in your pocket instead of a bag. And it's the reason the electric car finally came back from the dead. The car Edison bet on in 1901 was right all along. It was just waiting for 100 years on a good enough battery. Which brings us to the last piece, and this is the strangest one, the part that reframes everything you just watched. Because after all of that, 2,000 years, a dozen countries, a Nobel Prize, you'd assume the battery is a solved problem. Finished technology. It is not even close. And here's the twist that ties the whole story together. That principle Volta found in 1800 is two metals, an electrolyte, electrons taking the long way around. We have never actually replaced it. Not once. In 220 years, we have gotten spectacularly good at choosing the metals. We have never changed the game. Every battery on Earth, including the most advanced cell in the most expensive electric car, is still just running Volta's move from that tower of coins. And that has a consequence most people never notice. We tend to think the engine or the microchip is what limits the future. It isn't. It's the battery. Think about it. We can etch billions of switches onto a chip the size of your fingernail, but we still cannot store enough energy, lightly enough, to fly you across an ocean on electricity. A tank of jet fuel holds dozens of times more energy per kilogram than the best battery ever built. That single fact is why your electric car has a range limit. It's why planes still burn kerosene. It's why the power grid can't yet run fully on wind and sun. Because the sun sets and we don't have a good enough way to store the day's energy for the night. Every one of those problems is the same problem. The battery. The humble, ancient, barely changed battery. That's why the race is more desperate now than ever. Companies are pouring tens of billions into solid-state batteries, trying to make the wet middle solid to pack in more energy without the fire risk. Others are betting on sodium instead of lithium. Heavier, but cheap and almost everywhere. In China, one company just switched on a grid battery running on sodium the size of 15 soccer fields, storing enough to power thousands of homes through the night. And there's a cost to all this we rarely see. That lithium doesn't come from nowhere. Much of it is pumped as salty brine from beneath the deserts of South America and left to evaporate in vast turquoise ponds you can see from space. They call it white gold, and whole national economies now ride on it. The cobalt in Goodenough's recipe comes largely from one country in Central Africa, under conditions that have become one of the ugliest supply chains on Earth. The clean, silent battery in your pocket has a very physical footprint somewhere you'll never see. We have been promised the next great battery breakthrough for 50 straight years. And mostly what we get is another small, hard-won refinement of the same 200-year-old idea. The frontier of the entire future, electric flight, a clean grid, cars that never touch gas, is still quietly Volta's stack of coins, waiting for someone to truly improve on it. So think back to you on the floor at 2 a.m., cursing at 4% and clawing for a charger. That flat little slab you're so annoyed at is not a modern miracle. It's the finish line of a relay that started with a misread clay jar, ran through a jar that could stop your heart and a pile of twitching frog legs, got refined by Daniell and Grove and Planté and Edison, watched the electric car live and die and live again, and was finally handed to you by 3 men and a Nobel Prize. 2,000 years of humans arguing with metal so that your screen can light up in the dark. And the strangest thought of all? That relay isn't finished. The battery is still the single thing standing between us and the future we keep imagining. Electric skies, a clean grid, an end to burning things for power. The next runner hasn't taken the baton yet. It might be a lab in Japan or a startup in a garage. It might honestly be someone like you. So the next time your phone hits 1% and dies, maybe don't curse it. You're holding the unfinished end of one of the longest, strangest inventions in human history. We've been chasing it for 2,000 years, and we're still not done.